Welcome back. This is the second lecture of the second session of the lecture series at CMI as a part of our S.T.E.M.S campaign. The lecture is by Aditya Raut. He is the third year undergrad student at CMI. He has represented India at the Asian Science Camp in Malaysia and won the silver medal in Asian Pacific Maths Olympiad. He will be introducing the concept of recurrence relation from this talk. I invite Aditya to start this lecture.
Hello, I'm Aditya Raut, and I hope you guys watch movies because the very first thing is a game from a movie called Planet of the Apes. How many of you guys have seen Planet of the Apes? Oh, great, you guys watch lots of movies. That's cool. Great, so the puzzle goes like this. There are 3 pegs. Okay, I'm gonna name them A, B, C. What's inside those pegs are disks. So it's like if you see the disk from top, it looks like this. Okay. So how they judge intelligence of apes is, so the game is you want to move all these disks from peg A to peg C, right? You want to move from peg A to C such that none of your moves should be placing a larger disk on a smaller disk. Okay? At a time, you can move one disk from one peg to the other, but like you can only remove the top disk, as you can see from this stack. At no point, you should place a smaller disk on a larger disk. And you want to move all disks from peg A to peg C. That's the game. You guys understand? So there's a formula for the minimum number of moves, which is the goal of this talk. We are going to calculate that. We're going to prove why it's the smallest. But so based on in how many moves an ape solves this puzzle, they judge the intelligence level. They test out drugs on the apes. And then the guy that solves it in the smallest number of moves takes over the planet. So it's a really good way, I guess, to judge intelligence of people. So let's look at smaller examples, since 4 disks looks like too much. Say if I had just one disk in peg A, in how many moves can I move from A to C? One move, right? You just move this disk from A to C. But if I had 2, can you give me the minimum number of moves required? 3. May I know the 3 from someone? Yeah.
3 moves.
How exactly? Okay, so let's just number these disks 1, 2, 3, 4. This will be 1, 2. Tell me the move.
So you take 1 to B,
1 to B,
2 to C, then 1 to C.
Right. So the moves, I'll list them here. 1 goes to A. 1 goes to B. Then 2 goes to C. And finally, 1 goes to B. C. So what happened in the end was, all this exact thing was moved from A to C. So for one disk, now let's make a table. Number of disks and moves. So there was one disk and we required just one move. There were 2 disks, we required 3 moves. Do you guys want to try out for 3 disks? Yeah, try out. Tell me the number if you have an answer. So now we have 3 disks labeled 1, 2, 3. We want to move all of them from A to C. What's your answer, first of all? 6 moves, okay. 5, okay, that's cool. Someone who can do it in 5, can you tell me your process?
So you move the first peg to B.
1 to B, okay.
Second one to C.
To C.
Then first one again to C.
First one again to C.
And then move the Wait, I'm not.
Yeah.
So we can place a bigger one on smaller ones, right?
No.
Oh.
You can't place a large ring on a smaller disk. But they don't have to be immediate. Like I can place 1 on 3, 1 on 2, but I can't place 2 on 1 or 3 on 1. Yeah? What's your answer first of all? How many moves? Okay. 6. Right, 5. Yeah, tell me the process for 5.
You move 1 to B,
Mm-hmm.
and then 2 also to B.
No, you can't.
You can't move to
Yeah, because 1 is here. You can't place a larger disk on it. So that's not allowed. Yeah.
You move 1 to C,
Okay.
then 2 to B,
Okay.
1 to B,
Mm-hmm.
3 to C,
Right.
and then 1,
Yeah. He's on the right track. Yeah.
1
Then
to
move
A,
1 to A.
1 to A,
Uh-huh.
2 to C.
B to C, and 1 to C.
Okay. Right. So the answer for 3 is actually going to be 7. We're going to prove it can't be done in less than 7. Does any of you notice a pattern here? Can you guess the answer for 4? He said 15. Yeah, you could notice pattern like 1, 3, 7, 11. I don't know. But yeah, the answer is going to be 15 for 4. And from the process that we're going to get the answer, we're going to also get the process of actually doing these moves. Right. So you understood the game, right? Doesn't look like something we would come across in real life. Apes definitely would. But yeah, so this exactly, this is like the first example someone gives when they talk about recurrence relations, which I'm gonna tell you what they are. But you get the idea that it's firstly a question from real life, a puzzle for which we develop theory. This you can try out on your own and maybe do in some number of moves. Now, if you do it in 15, you are smarter than the normal apes. So this I'm gonna keep on one side, and we're gonna return to this after we have developed what are recurrence relations. So you guys have come across sequences and series as such, right? What recurrences actually mean are, if I'm denoting the nth term of my sequence by an, recurrence, if you have heard the word before, you must have heard in recurring decimals. So it's like something that keeps happening, repeating. So recurrence relation for a sequence tells you what is the empirical formula for the sequence, what's the rule that it keeps following. For example, I have this sequence. If I ask you the next term, you say it's going to be 9. Because there's some relation you see, which is like, for here, you can say you're adding 2 to every previous term, and you're getting the next term. So, yeah.
What's an empirical formula?
Yes. So it's like a general relation that your sequence is going to follow. For example, now this is the nth term, right? Do you see I can write this as an equal to an minus 1 plus 2. What this means is nth term is obtained by adding 2 to the n minus 1th term. Is that what this formula follows? Does everyone understand this? Now, there's one, let's do one more. Must have seen this before. What will be the next term? Yeah. Can you tell me in terms of previous terms how this one will look like? What are you doing to get the next term? Multiplying by 2 the previous term. So what should I write here? Yeah, 2 an minus 1. So it's 2 times of the previous term is the next term. So you see, now given this, just this is not enough because it's a rule that my recurrence is going to follow. I need some additional information to determine what the values are going to be, right? If I gave you the first term, I told you A1 is 1, and I gave you this formula. Do you see you can get the entire sequence? So I don't have to write this whole infinite sequence. I can just give you the initial value and this relation, and that is going to be sufficient. I can tell you the entire sequence just based on these. So initial values and some necessary information determine your sequence completely. Okay? So why we are introducing this is, in general, when you come across a problem, you would want to solve a smaller problem first. Maybe instead of solving for n, it's easier to solve for n minus 1. In that case, you know the answer for n minus 1. If you know how to move from the answer for n minus 1 to the answer for n, which will be some sort of a recurrence, a dependence of your answer on previous or smaller problems answers, then that's going to give you a recurrence relation, the dependence. And solving for smaller problems is easy. Say if I have to select 10 people from a group of 100. Now, selecting from a group of 10 is easy. I take all of them. If I can tell you how n depends on n minus 1, number of ways of choosing out of 100 people, how it depends on out of choosing 90 from 99 people. Now, that's going to give you a relation, and that makes your life easier. So the whole idea of recurrence relations is to find the dependence with smaller problems and then solve the smaller problem which is easy to solve so that we don't have to solve the last problem. Do you guys get the idea of what recurrence relations do? So I'm going to write one more example. It's a very famous sequence. I want you to notice what's happening here. Sum of the previous two. So what will be the nth term of this sequence? Does everyone understand this? So you see how recurrence is set up just by looking at this sequence. Now, I know, say A1 is 1, and that's how it started. But if I ask you what is the 1000th term, can you give me the answer? So now my question is, what is A1000 for all these sequences? Which ones do you think you can answer right now? The value of A1000 for this is our sequence 1, sequence 2, and sequence 3. Can you give me the answer for any three? Any of the three? First one, yeah, what's the answer? So for this sequence, the answer is going to be 1999. This one is going to be 2 power 1000 minus 1, so 2 power 999. Do you notice it here? Nth term is 2 power n minus 1. First term is 2 power 0, 2 power 1, 2 power 2, and so on. Now this, here you can give me the answer for A1000 directly because you are able to see what a term is without its dependence on previous terms, right? Here, for example, you see that every time you are adding 2. So for the 1000th term, you would add 2 999 times. So 999 into 2 plus 1, that's this number. So you are able to determine the value of value at some point directly because you know what the sequence is without its dependence formula. So that is called a closed form. So closed form is the solution for a recurrence. Here we have written a relation if I'm able to give you, so now if I ask you a 1000, you'll actually have to calculate all those, right? Because right now we can't see how it depends. Exactly. And the general formula looks very ugly. I'll just write it down here. It's 1 over root 5, 1 plus root 5 by 2 power n minus 1 minus root 5 by 2 power n. This doesn't look like they would be integers, right? Like, not a priori. But these we know definitely are going to be integers. So these are also going to be integers. How we come across this formula is by getting the closed form, which we'll discuss later. So you guys understand what happened in these sequences, how recurrence relation was set up, and how getting a closed form can make your life easier. Okay. Now we'll move on to real life puzzles again. Right. So now I have a staircase with say 10 steps. Okay. I'll start here. Seeing how long my legs are, I can go either 1 step at a time or I can go 2 steps at a time. I can't go 3. I want to calculate in how many ways I can go from the bottom step to the 10th step. Do you understand the problem? We want to keep going up. At every step we can go either by 1 or by 2. Now I want to go up 10 steps. So like one way would be just take 1 step at a time 10 times. Or I could do 2 steps at a time 5 times. But I could do some sort of a combination, and that would be a different way, right? So you understand this problem is not something you can just tell me orally directly, right? However, if I ask you just for 3 steps, do you think you can tell me, try to list out number of ways of going from this to the 3rd step by going 1 or 2 at a time? Yeah? 3 ways. Can you list out as a sequence of 1s and 2s? 2, 1. 1, 1, 1. 1, 2. Yeah. Do you see that these are the only 3 ways of going? Now, solving for a smaller problem is easier. If I can give you the dependence on these, and I am asking you, say, A10, do you see that calculating A10 manually will be easier with a formula of previous sorts? Like if I give you just relation, one-line relation between an minus 1, an minus 2, some number of terms. That is going to be easier. Does everyone notice this? We are actually going to do that. So this is my nth step. Okay. An, I am going to define it as, so this means define. You must have seen equality. If it's preceded by a colon, it means define. So an is defined as number of ways of climbing n steps with a rule of 1 or 2 at a time. So now tell me, how can I get to the nth step? From where all can I come to the nth step? Right. You can come from the step before or the one before that. Do you see that I cannot come to this step from here directly? I have to go here or here. Right? So, every way of coming to the nth step, I can classify into 2 different parts. One is, I am taking a step from here to here directly. Right? I can come to the n minus 1th step and then take 1 step to reach n. Or I can come to n minus 2 and take one step of, 2, skipping 1. So do you see that these are the only ways of going to nth step? So number of ways of coming to the nth step is actually number of ways of coming to the step before. Just take one step after that. I can't do anything else. If I take 2, I'll go to the n plus 1th, which I don't want. So there's only one way to go from n minus 1 to n. And if I'm going from n minus 2 to n, I can either come like this, but that I've already counted when I came to n minus 1. So now I want to go from n minus 2 to here. There's only one way. Take the 2 step. So do you remember this? This was exactly the relation for the third sequence that I wrote. So let's calculate for smaller numbers. If there's just one step, I'm starting from here. How many ways are there to go? 1. So A1 is 1. If there are 2 steps, in how many ways can I go? 2. So A2 is 2. Like this or like this. If you remember, A3, he just told us, was 3. Do you see it's the addition of 1 and 2? So if I actually wrote the sequence, it's going to be 1, 2, 3, 5, 8, 11, 13, 21, 34, 55. Do you see this is way easier to calculate? If you were to list out sequences of 1s and 2s for 10 steps, it's going to take quite a while. But by understanding the relation between n and the previous ones, we made the problem smaller. Like now we are able to calculate it. Now, even next step, if we can get the closed form for this relation, then I can tell you the answer right now for 1000 steps. So first, we reduce the problem from actually listing down 1s and 2s to getting this relation and then calculating. Now, even calculating can be a tough part, but if I get a closed form, that problem is also solved. So that's what I want you to take away from this. The general idea of getting recurrence relations is smaller problems are easier to solve, and by knowing the dependence, we can calculate larger ones easily. So this sequence is very popular. It's called the Fibonacci sequence. Every term is the addition of previous 2 terms. The sequence is so popular and studied in so much detail that there can be like a 2-hour lecture on just this sequence. In how many different problems it appears, how the terms are related, all sorts of things. But we're not going to go into that. We're going to go into recurrence relations. So that's the thing about Fibonacci sequence. The classic problem is n steps going 1 or 2 at a time. If I ask one taller friend of mine, and he can do even 3 steps at once instead of 1 and 2, do you see that you can still solve the problem pretty easier? Now the question is, I can go 1, 2, or 3 steps at a time. In how many ways can I go n steps? Can you give me such a relation?
Plus a n minus 3.
Okay. Anything
a
else?
n minus 1 plus a n minus 2 plus a n minus 3.
Yes. Does everyone see why that is true? Because when I come to n minus 3 now, if I do this, I have already counted in a n minus 2. If I do this, I've already counted in a n minus 1. So the only new way that I'm getting now is go directly from n minus 3 to n. So if I'm now allowing 3 steps, this is just going to be plus a n minus 3. Do you see that if I calculate the first 3 values, a1, a2, a3, after that, calculating a4 I can do from here. a5 I can calculate from a4, a3, a2, and so on. So the idea of a recurrence relation is to have this calculation part done easily. So in general, in computer science, if you fed this problem to a computer, okay, and you asked it to list down sequences of 1s and 2s. It will actually have to go through all combinations, right? But if I fed it this formula, at a time it's only taking in 3 numbers, giving the sum as the next answer. And then taking these 3, giving the sum as the next answer. You see that the calculation is way faster now. So that's the power of recurrence relations. So do you guys want to see the apes problem now? How we relate it to this? Okay. So in any problem that you come across, it always makes sense to understand how an extreme case works out. So what do I mean by an extreme case? Say I'm doing a sequence of moves. What happens in the last move? Or some special move at which I have some specific configuration. So if I have now, let's move on to the general one directly. I claim that for n disks, 2 power n minus 1 is the answer. Do you see it holds here? So for 1, 2, 3, 4, you see these are 2 power n minus 1. So that's my claim. For n, it's going to be 2 power n minus 1. So I have n disks here. N disks in A. B, C are initially empty. Okay. I want to move all disks from A to C. Like I don't want anyone remaining here in the end, right? So I have to move the last disk as well. Do you see this is some sort of an extreme case? Like this is the last biggest disk. So this is sort of like an extreme case. So when I have to move this last case, what can the rest of the configuration be? We know we can't move a larger disk on top of a smaller disk. This is the largest. So the last peg must be empty. Does everyone see that? When I'm moving this largest disk, the last peg must be empty. Also, I can only remove the top disk. So what does that tell you about this peg A?
I have a question.
Mm-hmm.
For the number of disks and moves,
Yeah.
n won't it be 2 power n minus 1 minus 1?
So, 2 power 4 is 16. So for 4 disks, the answer is this. So for 2 disks, you remember it was 3. So it is 2 power n minus 1. Is your doubt cleared?
Because for 1 disk it's 1, but 2 power 1 is 2.
Yeah.
But you have only 1 move.
So 2 power 1 minus 1. 2 power n minus 1. So it'll be 2 minus 1, that's just 1. Okay, great. So when I'm moving this last disk, I know that C peg must be empty entirely. Also, I know that nothing can be on top of the last disk because I want to move it. What does that tell you about the other disks? All of them have to be in B. Okay. Now look at this problem. There's nothing special about pegs B and C. Number of moves to get something from A to C is actually going to be the same as going from A to C, A to B. Because whatever move I was doing to B, I'll now do to C. And whatever I was moving to C, I'll move to B instead. Is that okay? So it's like I am relabeling this as C and this as B. Does that make a difference to my problem? If I am seeing 3 pegs in front of me, it doesn't make a difference how I label them. What actually matters is how I put the disks, right? So now we know that when moving this disk, it is some intermediate step. We don't know how many moves we did before that just yet. But we know that we are going to eventually reach a state when I have the largest disk here. So we were naming these by 1, 2 up to n, right? So n is going to be in A. All of 1, 2 up to n minus 1 are going to be in B. And C is going to be empty. This is an intermediate step that we definitely have to reach. Do you see this? So by looking at this extreme case, we have cut down the problem to some specific thing. Like this is a state that I have to reach. Now I'm going to define an, and that will make, like you'll see how it depends now. An, I'm not going to define as number of moves to go from A to C n-1 disks. I am going to define it as minimum number of moves. To go from, okay, to move n disks from A to C. That's my definition of an now. Do you see that in this definition I can make this A to B? It won't make a difference. Okay? See what has happened here. I have actually moved the first n-1 disks from A to B. Do you know what is the minimum number of moves to do that? Minimum number of moves required to move n-1 disks from A to B. It is an-1. Because moving from A to C, same number of moves is going to be same as moving from A to B. So at this point, from reaching from here to here, the minimum number of moves I can do is an-1. Because technically, this large disk hasn't moved at all. So if this wasn't here, it's like solving the problem for n-1. It's not here anyway. So you moved this top n-1 part from A to B directly. So we know the minimum number of moves, we just defined it. So it's going to be an-1. What happens after this? You have to move this largest disk to C. So that's one move. After one move, you are left with an empty a B with n-1 disks, and a C with the largest disk. What do I do after this? It's the same problem for n-1 again. You have to move these n-1 disks from B to C. And that's actually going to be the same as moving from A to C, because there's nothing special about these pegs. So after this, I'm going to do an-1 more moves, and that's going to solve my problem. Are you convinced that this has to be the minimum number of moves? So the proof why this is, like I just defined it to be minimum number, right? But it's not necessary whatever I define is true. I'll just define this person's height is 14 meters. That's not true. But why I defined it as minimum number of moves was this recurrence actually tells you it has to be minimum. Why? This intermediate step is necessary. You cannot avoid this state. We just did the argument for that, right? Now if this state is necessary, and you know the minimum number of moves of coming here is an-1, and after this whole thing is like fixed. So this state, which we found by looking at the extreme cases, it has now told you that an has to be first an-1 moves of moving these n-1 disks, then one move where you move the larger disk here, and then again an-1. So an is 2 times of an-1 plus 1. Is everyone convinced with this recurrence relation? Now we'll calculate it and get the closed form. So after this we can discuss techniques of getting the closed form. Now how to get this 2 power n minus 1? Because I have claimed it to be something that doesn't depend on previous terms, right? This number 2 power n minus 1, it doesn't take into account what was the answer for an minus 1. So I want to get that form. What do I know already? That a1 is 1. This I know. Do you agree that this much information is enough to determine the entire sequence. Telling you the first term and giving this relation gives me the entire sequence, right? So this should be enough to get the general form because this defines the sequence completely. So let's try that. What is an minus 1? Do you see that if this is the formula for an, the formula for an minus 1 is going to be 2an minus 2 plus 1. Because every term is 2 times of the previous term plus 1. So n minus 1th term is 2 times of n minus 2th term plus 1. So I can write here 2 times of an minus 2 plus 1 and the plus 1 directly from there. I have just replaced an minus 1 with this, which we know from the recurrence relation. Okay? What will be the next step? 2 times of an minus 3 plus 1 plus 1 plus 1. Is that fine? Now we need to notice what exactly is happening when we expand this. So notice that this is 4 times of an minus 2 plus 2 plus 1. Yes. This next one is 8 times of an minus 3 plus 4 plus 2 plus 1. Do you see a pattern of what this expansion is going to give? Every time this index goes down by 1, this power of 2 increases by 1. So I'll just write one more. Right? So all these plus ones, last one is not multiplied by anything. This second last one is multiplied by this 2 only. This one is multiplied by this and this. So you are adding powers of 2, sort of. So this next one is going to be 16 an minus 4 plus 8, 4, 2, 1. Okay? So can you guess now? So by doing this, we are going to reach at a1. So when we moved from n to n minus 2, we decreased the power by 2. So when we move from n to 1, we decrease the power by n minus 1. So what we are eventually going to end up with is 2 power n minus 1 times a1 plus all these smaller powers of 2 added. Okay? And what is a1? a1 I know is 1. So have I solved the problem for an? Because now I have this formula that an is 2 power n minus 1 plus 2 power n minus 2, so on till 4 plus 2 plus 1. This is a summation that does not depend on previous terms now. And this sum is 2 power n minus 1. Like, try adding if you want. If you add 1 and some powers of 2, it's actually the next power of 2 minus 1. That is a geometric progressions sum, which we'll do next. But now I have solved the problem for the... So this problem, Planet of the Apes problem, is actually called Tower of Hanoi. And this was worked on for a long time until people came up with solutions. This is not the only solution. There are way many ways to solve this. But this is one of them. And do you see, from this, you actually get how to do these moves. Because if you know how to do for n minus 1, you know how to move from there to n. And you know how to do for 1. So you're going to keep working on that and get the answer. Okay? So that was our claim. For n disks, you can do it in, you cannot do it in less than 2 power n minus 1 moves. Okay? So now try thinking about how you do it in 7. You guys had ideas about 5 and 6, right? You see it can't be done in 5 or 6 moves. Okay. So now, after getting the recurrence, how we solved it was substituting the previous terms, right? Luckily, we got some sort of a series which we can sum. 1, 2, 2 square, so on, sum till 2 power n minus 1. We may not always get that, but there are some forms of the recurrence relation for which you get this sort of a thing. So we'll move into finding the closed form for this. So now for that we need what's called homogeneous recurrence relations. So you guys have heard of homogeneous mixtures, right? What are homogeneous mixtures? Like it's the same thing everywhere. It's uniform sort of, right? So homogeneous recurrence relations are where everything is of one form. It's like if I have an, it's going to depend on things like an minus 2, an minus 1. These can be any number, but they all have to be from this sequence. You see that all of them are of one form, right? A number from your sequence. So this is a linear homogeneous recurrence relation. So linear in general means everything has power 1. So quadratic has power 2. So if I had squared these, something like this, then it would be a quadratic homogeneous recurrence relation. What homogeneous means is everything should be of the same form. Now, for example, for the Tower of Hanoi, what we got the relation was this. 1 a priori is not something, not a term of your sequence, right? It's not some general formula that you can use for any n. So it's like, but for the Fibonacci sequence, we had this formula. And here everything is of the same form. So when you have a linear homogeneous recurrence relation, life gets easier. My claim is we can convert this into a form like this. So so this equation, this linear relation, is not a homogeneous recurrence relation because not all terms are of the same form. But we can convert it to that form. Let's see how to do that. Can you tell me what is a n minus 1? 2 a n minus 2 plus 1. Both of these are true, right? Because the whole sequence follows my recurrence relation. If I subtract these, what do I end up with? an minus 1 on the left hand side. And here 2an minus 1 minus 2an minus 2. And 1 gets cancelled. Now you see that this has become homogeneous. Everything is of the same form. So when you reach this homogeneous form, after that you can work on it to get the general formula. But the idea is to convert these things into these forms. Okay? So that was homogeneous recurrence relations. Now let's see something called as characteristic equation. So how many of you are from 8th standard? Have you heard the term polynomial before? All of you have heard polynomials. Do you know about they can be factored? Okay, we'll see that. So next thing that we see is for a linear recurrence relation, we'll have a characteristic equation. What characteristic equation means is you have firstly a recurrence of this form. You want to make it into a polynomial because we know how to deal with polynomials. So what you basically do is replace an by x power n. Have you seen these sorts of terms before? X power n. So this now becomes this, right? If an was something like x power n, this is how it looks. I'll take x power n minus 2 common. So this becomes x square. And this side we have x plus 1. Is this taking out common factors known to you guys? So I can take out x as a common factor on both sides. If x is non-zero, I can cancel it. I can do it at most n minus 2 times. Now I remain with x square is equal to x plus 1. This, what I am remaining with in the end, it's an equation. One side is a polynomial. Okay. So when you end up with polynomials, their roots give the general formula. If you guys don't know what roots are, we can just totally skip this part. So now I need a show of hands. How many of you have seen quadratic equations before? Okay. So people who don't know quadratic equations, just look at it, because eventually you're gonna come across this anyway. So take it with a grain of salt, it's okay. This, can you find the roots to this quadratic equation? You know some formula, right? Minus b plus minus root of something, something, something. Yeah. So when you have a quadratic equation, we know how to find its roots. The idea is, when you have a linear recurrence relation, you make it into a polynomial. It has some roots. The general formula for an can be written in terms of those roots of the polynomial. So this, for example, if I were to convert this into a polynomial, okay, what is this? This is an equal to 3a n minus 1 minus 2a n minus 2, right? This is the exact same thing. So they all convey the exact same information, because from this I wrote this. Subtracting these two, I got the third equation, and that one I have rewritten here. If I were to make a polynomial out of this, what will it be? Do you see it will be x square equal to 3x minus 2. Same process as this, replace an by x power n. Okay, so this, now I end up with a quadratic polynomial, x square minus 3x plus 2 equal to 0. Do you guys know the roots of this? 1 and 2. So people who don't know about roots, they are the values for which this is satisfied. You see, if I put x equal to 1, this becomes true, right? 1 minus 3 plus 2, that's 0. If I put the value 2, this becomes 4 minus 6 plus 2, that's also 0. So so now this is a polynomial of degree 2, which is why it has two roots, 1 and 2. If you remember the general formula for our an, it was 2 power n minus 1. I can see this as 2 power n minus 1 power n, because 1 power n is 1, right? So you see that general formula is somehow related to roots of the polynomial. So your entire sequence, the general formula depends on this, which was obtained from such an equation. So it's like a characteristic of your entire sequence. That's why these equations are called characteristic equations, because they define a character of your entire sequence. And then you can get this formula in terms of the roots. Is the idea clear? If you're not comfortable with equations or roots, it's okay. What we are doing is, we are converting a recurrence relation to polynomials, getting their roots and expressing the solution in some form. That's what we are doing. So I'll move on to one more problem, some real life puzzle sort of a thing. And when we calculate for that, you'll find it better. So the question is very interesting, what you would usually see in some general mental ability tests. Do you have a doubt? Okay. So a plus b plus c is 1. A square plus b square plus c square is 2. A cube plus b cube plus c cube is 3. Okay. You know, in general, when you have n variables, you need n equations to know what they are. They have to be consistent. They have to give you information. They can't be giving you the same information twice. All those things, right? So this is, we have a, b, c, that are 3 variables, and these are 3 equations. So technically, you should be able to solve for these from these 3, right? My question is, what is a power 4 plus b power 4 plus c power 4? Any guesses? Okay, so now we're going to find a way of doing this with just algebra without using anything new. But then you'll see how recurrence relations play a very important role. So first of all, whenever you come across a problem and you feel like you can't approach it, make it into a smaller problem. Say instead of these 3 A, B, C's, we just had 2, A and B. Say problem was something like this. A plus B is 1. A square plus B square is 2. What is A cube plus B cube? This, I'm pretty sure you guys have come across the factorization for this identity. What is A cube plus B cube? A plus B. Yeah, A square plus B square minus AB. That's the thing, right? So this is a factorization of A cube plus B cube based on these. From these two, if I calculate the value of AB, do I know the value of A cube plus B cube? Right? How do I calculate AB from this? Right. So this everyone knows, A plus B whole squared. This is A squared plus B squared plus 2AB. Right? What is A plus B? 1. A squared plus B squared? 2. So now I know 1 plus 1 is 2 plus 2AB. So AB is minus half. Right? Do I know the value for A cube plus B cube? Is going to be 1 into 2 minus half. So it will be 2 plus half, or 2.5, 5 by 2. Okay? So we are solving this from some identity on smaller powers. Okay? How I am going to convert this in our problem is, notice that this is A plus B times A square plus B square minus AB times A plus B. Why am I doing this? If I define A power n plus B power n as Tn, this what it's saying is T3 is A plus B times T2 minus AB times T1. What I am telling you is, you can have Tn is A plus B Tn minus 1 minus AB Tn minus 2. Can you think of this? So it's very easy to see if I have defined, so yeah, let's write the definition here. Tn is A power n plus B power n. Okay. Now this is A plus B power, A power n plus B power n. This is what we want in the LHS. RHS is A plus B, A power, okay. This is LHS. RHS is a plus b, a power n minus 1, b power n minus 1, minus ab, a power n minus 2, b power n minus 2. Is everyone comfortable with this? So I'm just writing this Tn as this. Do you see these two are the same? This, if you expand, is going to be a power n plus a b power n minus 1 plus b a power n minus 1 plus b power n. And these two terms are exactly what you're subtracting. So these two get cancelled with this. So you remain with a power n plus b power n, which was exactly LHS. So we know that Tn is a plus b times Tn minus 1 minus ab times Tn minus 2. Now do you see, if I asked you what is a power 10 plus b power 10, you don't have to do this sort of algebra because you already calculated the value for ab. You now know that Tn is Tn minus 1 plus half Tn minus 2. Do you see that? Because minus ab is just half. So now you have converted one difficult algebra problem into a recurrence relation. And calculating for smaller values, you can just do manually, right? If someone asked you what is a power 20 plus b power 20, it's now easier. So what we want to do for this problem is again convert it into a recurrence relation. And so we can see two ways of doing that. One will be this algebraic ugly way, but that ugly way is going to give the general formula for getting nth term. Okay? So let's first calculate a power 4, b power 4, c power 4. So if I were to do this, this will give me a power 4, b power 4, c power 4 and some extra terms. I want to get rid of those extra terms, right? So this will be Is there anything else? So three terms, we have 9 terms here, okay? This part we want. This is some extra that we want to get rid of. So how we could tackle this is a plus b plus c into something. Let's do ab plus bc plus ca. So this is like algebraic manipulation. I know how to do this, which is why I am being able to write this term. You see that coming up with this randomly is not very intuitive. So algebraic way is not that intuitive. But this, if I write this, now I get some more extra terms which I have to subtract later. So this will give me, okay, these are degree 4, so I need, I'll do with a square plus b square c. Because here I had a plus b plus c, now I'll use this. Now I end up with a cube b plus a cube c, all these terms that I want. In addition to those, I have terms of this form, a square bc, b square ac, c square ab, right? These are the extra terms that I would get from this. So I subtract them. What do I see in common with these? This is minus abc times a plus b plus c. Okay? So this whole thing is these minus abc times a plus b plus c. Are you guys convinced with this manipulation? Okay. So do you see I have converted this into the previous 3 problems? All I need to know now is this value and this value, and then I'll be done. So this, now I'm gonna write Tn as a power n plus b power n plus c power n. What this means is T4 is a plus b plus c T3 minus ab plus bc plus ca T2 plus abc T1. Is this relation clear to everyone? I claim that I can replace this 1, 2, 3, 4 by n, n plus 1, n plus 2, n plus 3. So I can write Tn as this Tn minus 1 minus this Tn minus 2 and so on. So this problem, let's see. This value I know. It's 1. This value I don't know. I want to calculate. Remember how we calculated AB? We squared a plus b and that gave us something. So let's square a plus b plus c. What's the formula for this? Two times of ab plus bc plus ca. Is that right? I know this, I know this, I know this value. Yeah, so it's minus half. So this is minus half. I'll write T4 is T3 plus half T2 plus ABC T1. Now our task is to calculate ABC. Do you know some identity that has ABC? Have you seen something like this? Okay. What does that give? Plus long list of terms, right? Yeah. So this, yeah, a square plus b square plus c square. This is an algebraic identity. Has everyone seen this before? This was one of those later ones in the book that you just, ignore, because a plus b square is what matters. So it's okay. This doesn't matter that much. Now we know this. It's 3. This is minus 3abc. This part, 1. This is 2 minus half. So it's 2 plus half. Right? So now you have 3abc is equal to 3 minus 2 plus half. That's just half. So abc is 1 by 6. And now your life is simpler. So you got a recurrence relation, which is just, this is by 2 and T1 by 6. So what is a power 4 plus b power 4 plus c power 4? So it's 3 plus 1 plus 1 by 6. 4 plus 1 by 6. So this is not 4. Surprise. 4 plus 1 by 6. So if you see it in some sort of a puzzle, general mental ability, you would tick 4, right? 1, 2, 3, 4. But it's 25 by 6. Because 3 variables, you have enough information from 3 equations to determine other things. And it's not random logic always to just have 1, 2, 3 and then 4. The answer for this is 25 by 6. So by seeing how something depends on smaller or previous problems, getting this relation, you can solve larger problems. Now, from these 3, you calculate the next one. From T2, T3, T4, you can calculate T5. And that calculation is easy because we know the general formula now. Okay? So let's wrap up with that. Thank you for being here, but if you have any doubts related to this, I'll take questions now. If there's some part that you did not understand, want to be repeated? All right, so that's it. This, yeah?
A to the power of 4 plus B to the power of 4 plus C to the power of 4 is equal to 25 by 6. Can we also denote it in decimals?
Sure. It'll be 4.16 recurring, I guess. You can always do that. So we just need the exact value, and that we know surprisingly is not 4. Okay. Yeah. Thank you.
Yeah, so let's thank Aditya for this very interesting talk that he just presented. Apart from the talk, he's also one of the core members in organizing the S.T.E.M.S campaign. So we would also like to thank him for that. And that's it. Thank you.
If you want to learn more problem solving strategies like this, be sure to check out the courses on brilliant.org.